Bonjour, bienvenue à toutes et tous pour cet événement KM3NeT. Donc, tout d'abord, je me présente, Vincent Poirot, directeur adjoint scientifique à CNRS nucléaire et particules. Et donc aujourd'hui, on va assister à cet événement KM3NeT. Nous avons aussi l'honneur de recevoir Philippe Baptiste, ministre chargé de l'enseignement supérieur et de la recherche. Donc, vous allez voir que cet événement va être filmé, on va être en direct sur YouTube pour la chaîne En direct des labos. Et également, il y a un reportage en même temps.
Okay. I'll go. Okay. Yes? Yeah. Okay. Good afternoon, everybody. We are thrilled to be finally able to announce a very exciting result from the kilometer cube neutrino telescope, KM3NeT. In 10 minutes' time, at 5 p.m., we will reveal our remarkable signal from the cosmos detected by KM3NeT. At the same time, the results will be published online by Nature and featured on their cover. I'm Paschal Coyle, Director of Research from the Centre de Physique des Particules de Marseille, and I was spokesperson at the time of this observation. I'm here at the CNRS headquarters in Paris. With me is Miles Lindsey Clark, the technical project manager at the same time. In Amsterdam, we have Aart Heijboer who will be at the Nikhef headquarters, and Rosa Coniglione at the INFN headquarters in Rome. Together, the four of us will try to present you this remarkable result in 5-minute speeches. But first, myself and Miles will present the collaboration and how the telescope works. So this is the KM3NeT collaboration. So a warm welcome from everybody. This is an image from our recent collaboration meeting at UC Louvain in Belgium. The results we show were a great collaborative effort. These are the guys and gals that did all the work. In more detail, this is a map of our collaboration. We're now over 350 scientists from 21 countries and 68 institutes. So KM3NeT has many science topics it can address. The principal topic is the exploration of the neutrino universe. The other important topic, we collect so many neutrinos that we can really study the fundamental properties of the neutrino itself. The telescope, as you will see, is located deep at the bottom of the sea and also gives a fantastic opportunity for synergetic science with marine scientists who essentially we offer them an electric plug, an Ethernet connection, and they can connect whatever equipment they want to study the deep sea. The image that you see here is from the Batibot camera deployed on the Orca detector, where we have a real-time camera monitoring the deep sea. So, what are neutrinos? So neutrinos are one of the building blocks of matter, very fundamental particle. We have three types of neutrinos: the neutrino electron, the neutrino muon, and the neutrino tau. The neutrinos are very light, have a very light mass. For a long time, we thought the mass was zero. The mass we now know is very, very small, but too small that we haven't actually managed to measure it yet. And we don't know yet which of the three neutrinos are the heaviest or the lightest. Because they're so light, they do travel at the speed of light. The neutrinos, very importantly, only interact through the weak interaction. So this means they're very, very hard to catch. In fact, we call them ghost particles quite often when we're talking about them. They can travel through walls, all the way through the Earth, and they can travel all the way from the edge of the universe without being absorbed. In fact, neutrinos are the closest thing to nothing we can imagine, but they are key to fully understanding the workings of the universe. Our studies with neutrinos are firmly embedded in a new field of astronomy called multi-messenger astronomy, where we try to use other particles different from visible light to understand the extreme universe. So we make use of high energy photons, gamma rays, charged particles, cosmic rays, and of course the neutrinos. But the neutrinos are extra special. They don't have any charge, so they're not bent by magnetic fields. So when we measure the direction, they point back exactly to where they came from. This is not the case for the cosmic rays, which have a charge. With the neutrinos, we can also see much further in the universe because their interactions are so small, they do not get absorbed by dust or interactions with other particles. This is not the case for the gamma rays, which can interact with dust. So also with the neutrinos, we see really into the heart of the cataclysmic objects we're studying. They don't just come from the surface, they really come from inside. Unfortunately, we can't detect the neutrino itself, but what we can do is when we're lucky and a neutrino does happen to interact with seawater, it makes other particles, and those particles do have charge. And once we have a charged particle, it's very easy to detect the charged particles because they emit a blue Cherenkov radiation, which allows us to find them. So the name of our game is to build the largest telescopes we can build to catch some of these neutrinos. So in KM3NeT, we've built two giant telescopes, Orca, which is 2.5 kilometers deep offshore from the south of France, and the Arca telescope, 3.5 kilometers deep and 80 kilometers offshore. This little artistic animation shows the relative scales of the two detectors. The two big blocks are the Arca detector, optimized for the high energies, and the smaller block is the Orca detector, optimized for the lower energies. And just to get a feeling for the size of these telescopes, here we've compared them to the size of the Eiffel Tower and the size of the Leaning Tower of Pisa. A very good, so the detector is under construction. It's not finished yet, but nevertheless, we are able to take data with what we have already installed, and you'll see the first results of that today. We hope the construction will be finished before the end of the decade. So the results you see today will have been performed with 10% of our full detector. So now I'll pass the words to Miles, who tell us how we construct such a complex telescope at the bottom of the sea. Thank you, Miles.
Thank you, Pascal. Okay, so I'll try to tell you a bit more indeed about how we build our telescope, and for that I prepared a nice video. So I'm just waiting for it to start. Yeah, so we can start the video. Okay, so I'll start first by further illustrating the detection principle of KM3NeT, a bit like Pascal explained. So as an example here, you can see a neutrino traveling towards the Earth from the distant universe. And when these neutrinos interact with matter, they create secondary charged particles like muons. And when these particles travel through water at a speed higher than the speed of light, they create this Cherenkov glow, and that's what we're trying to measure. So KM3NeT consists of a three-dimensional array of optical modules arranged along very tall flexible lines, detection lines, 200 meter high for Orca, 700 meter high for Arca. We've deployed so far 57 of these lines on the seabed, but once completed, KM3NeT will comprise more than 300 detection lines, 6,000 optical modules, covering a total volume of more than 1 cubic kilometer, making it one of the largest neutrino telescopes in the world. So at the core of KM3NeT's detection system are the optical modules, as you can see here. Each of them has 31 optical sensors that allow us to read the steering of light. These sensors are assembled in half hemispheres that are designed to withstand the very extreme pressures of the abyss. We then seal these half hemispheres together. This is an optical module. We test it, we calibrate it. And then the next step is for each detection line to assemble 18 of these optical modules on an electro-optical cable. This is really the backbone of our detection lines. And one really interesting feature of our integration process are these spherical structure you see here, in which we carefully insert each of our optical modules and on which we wind the electro-optical cable I was talking about just before. And as you can see in this nice stop motion video. So once this sphere is completely loaded with our optical module, we attach it to an anchor. That's the big yellow part you see in the bottom. It's meant to keep the DU nice and grounded to the seabed. And then we deploy them on our two sites. So as Paschal said, 40 kilometers offshore Toulon for Arca in France and 80 kilometers offshore Sicily in Italy for Arca. So the lines are then carefully lowered at the depths of the Mediterranean Sea. That's a process that takes typically a couple of hours. It's quite deep, as Paschal said. In parallel, we also deploy these so-called remotely operated underwater vehicles. These are small submarines that we use to perform visual inspections and specific tasks at the bottom of the seabed. And once the detection lines reaches the seabed, as you can see in these nice pictures here, we connect them to our network of submarine cables and onto our junction boxes. And these junction boxes provide power to the line and allows for transmission of the data. So now the very exciting part. So how do we deploy that? We pull on a mechanical trigger, as you will see right now, and this releases completely the spherical structure. And this spherical structure has its own buoyancy, so it floats up and it unfurls completely the line from the bottom to the top, as you can see. So more than 700 meters for Arca, as I said. We then recover this spherical mechanical structure and we just simply build new DUs, new detection lines with them. So then, as you can see here, these are the optical modules in their final configuration, so vertical. We need to keep good track of their position, so we have compasses and we've built an acoustic positioning system developed specifically for KM3NeT. Once the detection lines are connected, all the data and the power transits through a main electro-optical cable, as you can see here. And this cable is attached to the shore stations. So we have one shore station for the Orca detector. This is the Michel Paschal Institute in south of France. And this is Capo Passero, south of Italy, for the Arca detector. So this is where all the optical fibers arrive. That's also where all the data is very carefully time calibrated with sub-nanosecond accuracy in order to reconstruct the track well. It's also where the power supply, the control, and the monitoring of the infrastructure is performed by the dedicated team. And finally, that's where the data generated by our detector is first checked and then processed by a team dedicated to software calibration and analysis. And they extract all the valuable scientific data from our telescope. So finally, it's important to highlight that we need a lot of people to build this huge detector. There's 30 integration sites involved in the construction of it. And that building such a large and complex telescope requires tremendous efforts and a great collaborative spirit. So now that you know a bit more about KM3NeT, it's time to unveil our discovery. So I leave the floor to Aart Heijboer, who was the science and software manager at the time of the discovery. So Aart, can you hear us from Amsterdam?
Yes, I can hear you. Yes, I hope you hear me too. Welcome everybody from Amsterdam. Greetings.
We cannot hear you, Aart.
Okay.
At least from Paris?
Yes,
can?
I think
okay.
I keep talking.
We can hear you, Aart. Let's go.
Okay, you can hear me. I start again. Greetings from Amsterdam. After these two beautiful introductions, it's my honor to announce that at this moment, or actually a few minutes ago, we are publishing in Nature the following article. I tried to switch the slides on my side, but that is not happening. Thank you. So in this paper, we report on the detection of a single elementary particle, a neutrino, and it is the neutrino with the highest energy ever detected in any observatory or experiment. Next slide, please. The energy of the neutrino is in the range above 100 peta-electron volt, a factor 30 larger than the highest energy neutrino detected so far. As such, this observation forms the start of exploring a new regime of energy for the highest energy cosmic accelerators in the universe. In my talk, I will briefly summarize the experimental result, what did we see, and then my colleague Rosa in Rome will discuss what we can say about the potential sources of this event. So next slide, please play the movie. In the middle of the night of February 13, 2023, the KM3NeT Aart detector detected the event that will be displayed here. What you see here is the detector, 21 detection lines, Eiffel Tower for scale, and the particle coming in from the right. And this computer program draws a colorful cone each time one of our sensors has detected a bit of light. In this movie, this has been slowed down by a factor 10 million. In the reality, this lasts only a couple of microseconds. And what we observed is a very distinct pattern of light that is characteristic for a charged particle traversing our detector. This particle is a muon, a heavier version of the electron, which is moving here at the speed of light. And the trajectory that was shown is reconstructed from all the observation times of the light on our sensors. Next slide, please. To give you an idea of the precision with which we do that, this is a plot from the paper, a little bit technical maybe, but here we compare the arrival time of the light on our sensors with the time when we would expect it given where we think the particle was. And what you can see in this histogram is that those two agree typically to a level of a couple of nanoseconds. And this is the case all through the detector. So at hundreds of meters away, on all the various detection lines of the detector, we see that the arrival time of the light agrees with the expectation from this flying particle to a precision of a couple of nanoseconds. Some photons arrive later. We also understand that. Sometimes the light scatters around in the water before reaching the detector. A prerequisite for such extreme precision is that we calibrate first the detector. For example, all the lines are moving with the sea currents, so we have an acoustic system to know with 10 centimeter accuracy exactly where each of our optical modules is at a given time. The conclusion here is that we can be extremely confident that we have seen a muon traversing the detector, and from the nanosecond precision timing, we can actually accurately reconstruct the direction very accurately. It turns out that the direction is that it is almost completely horizontal. And this is one of the things that makes this observation special. The fact that we have a muon is not so special. We have in 1 year 110 million muons, but those are all downgoing. Those are made in the upper atmosphere, and they are not so interesting. But when we see a horizontal muon, it is interesting, because muons can travel for some range through water, but not, as would be needed in this case, to 140 kilometers of water and rock. The only particles that can traverse those amounts of matter are in fact neutrinos. So purely from the direction of the muon, we can infer that there must have been a neutrino. Now, the other thing that makes our observation extremely special is the fact that this muon was extremely bright. So we just saw it on many, many sensors in our detector. Yeah, thank you. In fact, we saw it on roughly 1/3 of the sensors in the detector. To be precise, 3,672 sensors have seen this light. Please go back one slide. Yeah. And this is the number that we used to measure the energy of the detector. So what we do is very simple. We compare the number of sensors that have seen light, which is the dashed line over there, to simulations. And so what we see is that we have to simulate muons of 100 peta-electron volt, 100 PeV, in order to produce such amount of light in our detector. So the energy of this muon is in this range, 100 PeV, and doing then a proper statistical measurement, also taking into account the uncertainty, for example, on the water properties, we arrive at the measurement for the muon of 120 peta-electron volt PeV, plus or minus roughly a factor 2. So to put that a bit in context for the non-particle physicists, the highest energy accelerator that we have on Earth, the LHC accelerator at CERN, accelerates protons up to roughly 1% of 1 PeV. So that is a factor 10,000 less than this muon that we have observed here. And that's the muon. Of the neutrino, we can actually not say too much, except that it must have had an even higher energy. It can have interacted close to the detector or far away. But with some quite generic assumptions on the neutrino spectrum, we actually make an estimate that the neutrino energy has been 220 peta-electron volt, but with quite large error margins, as you can see. Yes. So in the paper, we compare the energy and this event to existing measurements of cosmic neutrinos. And so that is shown in this plot, which is also quite technical. On the y-axis, you see the flux. That is basically just the intensity, how many neutrinos fly by per second. And on the x-axis is the energy on a logarithmic scale. The data points on the left here are the previous measurements by the IceCube experiment. And our measurement is the blue data point on the right. So this indicates the energy range that I have just explained to you, but we also try to estimate how the intensity of neutrinos that this corresponds to. But since we have only one event, this has a huge error bar there, as you can see. What is very clear is that this is the first data point in a completely new energy range on the right of the plot, where there was nothing before. The previous highest energy neutrino ever observed is the red cross over there with the arrow pointing to it. It's at 6 PeV by the IceCube experiment, and we are a factor 30 above this. So what we have learned is that there are things in the cosmos that produce neutrinos of these extreme energies. The exact origin is still a matter of speculation, but I leave to my colleague Rosa to discuss some of the ideas of what it could be. Thank you very much.
So as Pascal briefly mentioned, I don't see the slides, the high energy neutrino, The high energy neutrino can be produced by several kinds of sources, in particular from galaxies with dense core or in the star environments. Here are listed some of the several kinds of sources that can produce neutrinos, and between them the active galactic nuclei, which are very luminous galaxies with a dense core, are actually the most promising ones. But we have another mechanism that can produce neutrino by energy. It's the cosmogenic mechanism. In the high energy cosmic rays, and in particular protons with very high energy, can interact with the photons in the intergalactic cosmic background, in particular with the cosmic microwave background, and can produce neutrino. These neutrinos arrive at Earth, in this case, as a diffuse flux, so without a privileged direction. And this is the most, let's say, one of the possible origin of our event. So this is the same plot that has been shown by Aart a few minutes ago, when there are superimposed some prediction from models and the projection at high energy of the IceCube data. The gray band is the model prediction for cosmogenic neutrinos, while the vanilla one are that one for the diffuse flux produced by extragalactic source populations. In our point, together with within the uncertainties, is compatible with both of them. And if we look the projection at high energy of ice cube, in this case the compatibility is poor, and this suggests that the event may have originated in a different cosmic accelerator than the lower energy neutrinos. We looked at the direction of this neutrino from it come from, and is reported in this map. This is a map in galactic coordinate of high energy photons. So how we see our sky when we look high energy photons. And this is the map from the Fermi-LAT collaboration. And in the center of this reference system, we have the center of our galaxy, the Milky Way, and the equatorial plane we see the galactic, the Milky Way plane. Our point is located in the right of this map, 10 degrees below the galactic plane, and is reported here. So to go more in detail, we look at in the same direction of the event in an area, in a zone of 3 degrees. 3 degrees. 3 degrees is our uncertainties in the pointing of the event. And we looked for intense and galactic sources. We didn't find any source on this area. We did the same work looking at outside our galaxies, and we have found 12 sources. They are all blazars. Blazars are a subset, let's say, of a particular kind of active galactic nuclei. But unfortunately, we have very poor correlation. No correlation was found with any of these sources. So we not claim that there is a correlation with a particular source in this case. These results, the collaboration today has also published several, what we call companion papers, several other papers on archive, where some of the results that are presented in the Nature paper are reported with more details. So, to conclude, we think that this discovery is a milestone in neutrino astronomy. This event is an event with the most energetic event detected so far, neutrino. This is 30 times higher than the highest neutrino energy detected so far, and it is the first in an explored region of great interest, in a region where neutrino are predicted but have never been seen. So, with the possible origin, as I said, are from cosmic accelerator, cosmogenic neutrino, but we cannot have firm conclusion. But we are sure that deploying more and more DU in the next year, we will have more and more data, and also the detector will increase in sensitivity. So more firm conclusion will come, may come, and soon we will improve also the pointing of our detector, and we will have a more precise determination of the position of this event. So for my side, it's okay. We are proud to be here, to share with you all these results, and we hope to have other occasions, maybe. So I give again the word to Paschal.
Can I go, or should I wait? Huh? Should I? Now. Okay, good. So, yeah, thank you, Miles, Aart, and Rosa, for those very nice presentations to present our remarkable result. Before we get to some questions from the audiences, I would like to thank, oh, it's me, yes. We would really like to thank all our major funding agencies that have contributed to the construction costs for building the telescope. These include Italy, France, the Netherlands, Spain, and Slovakia. In particular, for the locations where the sites are located, Italy and France, we've really had tremendous benefit from local and regional funding. And again, we really appreciate and thank you for your confidence and support. We also would like to thank the European Union, which have continuously supported us all during through all phases of our project, starting in fact, KM3NeT started around 2006 with in the design study phase, supported by Europe. Then we had preparatory phase. We're now kind of in the implementation phase with InfraDev support. So it's really, the European Union has really been instrumental in making KM3NeT happen and making these exciting results you've heard today. We would also like to thank all our many industrial suppliers. It's really not very easy to build such a big telescope in the deep sea, and we rely very much on a lot of high-tech companies around Europe and the world. And in many cases, we've had to develop bespoke solutions for us to be able to do what we can. So thanks again for everybody on this slide. Okay, so now we can pass to some questions. So I'm being fed questions through WhatsApp here. These are questions mainly from the people who are connected remotely via the YouTube channel. There will be the national events coming very soon, so people in the audiences can ask directly their question at that time. So one of the questions is for Rosa. What astrophysical source does the event originate from?
As I said, we cannot say.
I didn't pick the question.
As I said, we have a particular source that we can claim as a source of this neutrino.
I'm afraid we don't hear you here, Rosa.
They cannot hear?
Can you hear me now? We heard
well,
you, Rosa.
Perhaps while that technical bug might be fixed, there was another question. So essentially the question is, why do neutrinos give us information on the processes involved inside the accelerators? It's kind of a technical jargon, but neutrinos are the smoking gun for what astrophysicists call the hadronic processes. Neutrinos can only be made if there was a proton that had been accelerated inside the cosmic source. So it's really, they're the signature of this proton acceleration. For example, high-energy gammas, they can also be made in these hadronic processes, but they could also be made in what we call leptonic processes, where electrons have been accelerated. So neutrinos give us this vital information to tell us what type of particles were accelerated inside the object. I don't know if Rosa is
Can you hear me now?
audible or not.
Can you hear?
Okay. We should stop. I think we're running out of time, and there are no more questions. So I will now call the international part of this special day for KM3NeT finished. And don't forget that you can follow the national events. If your favorite language is Dutch, French, or Italian, you can continue on those YouTube channels. The English channel will now stop. And while the transition is happening, we'll like to leave you with a little video, short video, which just kind of summarizes everything you heard today. So thank you, everybody, and we're done. Thank you.
The universe is the stage for mysterious and violent phenomena, cataclysmic events, in which streams of particles, called cosmic rays, are created and then travel across the vast expanses of space. Cosmic rays are high-energy charged and neutral particles, including photons and neutrinos that reach the Earth from space. Neutrinos of extremely high energies can also be produced in the interactions of very energetic protons with the photons of the cosmic microwave background radiation that permeates the universe since its dawn. Neutrinos are elementary particles without electric charge, and so are not deflected by cosmic magnetic fields. As they are very light, they travel nearly at the speed of light. Due to their very weak interaction with matter, they are extraordinary messengers that carry with them valuable information from the heart of the most powerful cosmic accelerators and about the distant universe. On the 13th of February 2023, a very high-energy neutrino from the farthest reaches of the cosmos crossed the Earth's atmosphere and plunged into the Mediterranean Sea. Here, at a depth of 3,500 meters off the coast of Sicily, there is the KM3NeT Arca Observatory, a gigantic network of high-tech eyes. In the darkness of the abyss, it searches for the faint bluish light emitted by the particles produced by neutrino interactions. This is what happened to our neutrino when KM3NeT detected its signal. The signal of the most energetic elementary particle ever observed. From the depths of the Mediterranean Sea, KM3NeT continues its mission to explore the depths of the cosmos.